Hey everyone, my name is James, and today I'm going to be talking to you about math. More specifically, I'm going to be talking to you about my class, Foundations of Math, which is an introduction to proofwriting. So honestly, proofwriting can be a little scary at first because you're kind of thrown into a problem and you don't really know where to start. But that's what I'm kind of going to be showing you guys today is how to get started on these problems, how to approach them, and how to look at them. Proofwriting in general is a lot different than most other classes. It's a lot less computational because usually it's just a lot of formulas and plugging and chugging. But here in proofwriting, you'll actually learn why it works, why what you're plugging into that formula works. So the first thing you want to do when you get your problem is write your statement in an if-then format. This more easily shows you what you already know, your hypothesis, and what you're trying to show, which is the goal of your problem. The second and third step in this proofwriting guide is to explicitly state what you already know and what you already show. After this, you'll expand what you have for your know by writing out any relevant definitions, theorems, and formulas that relate to your know. Similarly, for your show, you'll expand what you've written and, again, expand any relevant theorems, formulas, definitions, etc. And finally, when you're writing a proof, when you first start out, you can test out your problem by choosing an example that satisfies your hypothesis and one that doesn't. So this will often give you an idea of the direction you can take your problem. So now I'm going to be taking you through a sample problem that I was assigned. So the problem I got was if the sequence an from n equals 1 to infinity is a bounded sequence of real numbers, and that every subsequence converges to the same limit L in the set of real numbers, then the sequence an also converges. So as you can see on the screen, I translated this into my know and my show, and I expanded my show to say that the absolute value of a sub n minus L is less than some epsilon, where n exists in the natural numbers and epsilon is greater than 0. This is the definition of convergence that I'll be using to complete my proof. So now to begin with the proof, we're going to start by creating a sequence z sub n, where z sub n is equal to the infimum of a sub n, where n is greater than or equal to k. To further expand this, I'll show that z sub 1 is equal to the infimum of the set a1, a2, and so on, and z2 is equal to the infimum of a2, a3, and so on. And similarly, I'm going to create a sequence y sub n, where y sub n is equal to the supremum of a sub n, where n is, again, greater than or equal to k. I also expanded that to allow you to conceptualize what's going on. And I guess the main point of this is that the limit of Zn as n approaches some number n1 is equal to the lim of a sub n, and the limit of y sub n as n approaches some n2 is equal to the lim sup of an. Okay, so to begin the actual proof, we're going to start off how we usually do. For epsilon greater than 0, there exists an n1 and n2 such that the absolute value of Zn minus L is less than epsilon for n greater than n1, and the absolute value of y sub n minus L is also less than epsilon for n greater than n2. We can do this because z sub n and y sub n are the lim-inf and lim-sup of an, which make up sequences, and we know that make up subsequences of a sub n. We know that from the problem statement and the hypothesis that all subsequences of a sub n converge to L. Also, it's important to note we should let n star equal the max of n1 and n2, so that when we fix n later on in our proof, little n is greater than n1 and little n is greater than n2. So because z sub n is equal to the inf of a sub n, and y sub n is equal to the sup of a sub n, by definition of inf and sup, z sub n is less than or equal to a sub n, which is less than or equal to y sub n. So if we subtract L, the limit, from this inequality, we get z sub n minus L is less than or equal to a sub n minus L, which is less than or equal to yn minus L. So to further expand this, I've copy and pasted what we did in the last slide. So for n greater than n star, which we define as the max of n1 and n2, the absolute value of zn minus L is less than epsilon, so negative epsilon is less than zn minus L, which is less than epsilon, and the same for yn minus L. So something important we can pull from that is that zn minus L is greater than negative epsilon, and yn minus L is less than epsilon. We can do this because z sub n and y sub n converge to their limit L. So because zn minus L is greater than negative epsilon, and yn minus L is less than epsilon, and zn minus L is less than or equal to an minus L, which is less than or equal to yn minus L, follows that negative epsilon is less than zn minus L, which is less than an minus L, which is less than y sub n minus L, which is less than epsilon. So we can cross out in this next line the what composes the lim inf and the lim sup, and then we are left with negative epsilon is less than or equal to an minus L, which is less than epsilon, and therefore the absolute value of an minus L is less than epsilon. Thus, for n greater than n star, a sub n, by definition of convergence, converges to the limit L, and our proof is complete. So after you finish, or you think you finish writing your proof, this slide presents a general checklist of what you can look for to make sure that you minimize the amount of flaws that are found in your proof. So for starters, your proof needs to define all variables that are used. Your proof needs to use words to explain each algebraic transformation that you do within your proof, which that just makes it easier for any readers to understand your thinking and for it to make sense to them. Also, your proof needs to clearly state where you're using your hypothesis or your no. And finally, your proof needs to state what method or approach you're trying to use. So for my approach, I didn't really specify it because I was doing direct, but I guess I should have done that. And finally, you need to make sure you cite like which definition explains like what you're saying or which theorem to effectively add credibility to your proof and explain what makes it valid. So yeah, that's all I have for you guys today, but I hope you had fun, and thank you very much for watching, and I hope you enjoyed.